I want to consider for a moment the scattering of light by the atmosphere, which is in fact related to why the sky is blue and the sunsets are red. Now, the fact that we look up in the sky and see any light at all is only because sunlight is absorbed and re-radiated in many directions, and that's called scattering. The light is scattered. You can kind of think of it simplistically as being reflected off the atmosphere. If there were no atmosphere, like on the moon or other places, there's no atmospheric molecules, there's nothing to scatter off, and the sky would be black, unless you're looking directly in the sun. So you see the sun from the moon, it would be very, very bright, but you look off to the right or left of it just a little bit, and there would be blackness. Kind of weird to think about. Okay, let's consider our late great planet Earth. That's unmodified here. Anyway, what I want to illustrate is the sun shining a beam of light through the atmosphere, and we're receiving it with our eyeball over here along the x-axis, and then we have the y and z axis as well. So we're considering these directions and the planes as shown here. Now here we have unpolarized light from the sun, and it's moving in the direction of the ray. And at this point, at the junction of the YZ plane, we have an oxygen or nitrogen molecule. The sunlight hits it, and it's going to often be scattered. Now when that happens, when it's scattered, it re-radiates the energy in a direction perpendicular to the direction of travel. All right, so I'm throwing this little graphic in here. Think of the sunlight as behind these atmospheric particles. Okay, so behind it, not above, like this kind of shows. But if it's behind it, then when the light is scattered, it radiates off perpendicularly, but in any direction, as you can see in the plane of the screen here, the plane of the screen in any direction. Does that make sense? So that would be along the YZ plane. So here's the YZ plane, and I'm now going to show the light that happened to be scattered from this particle. All right, and it's in the YZ plane. None of it's in the X plane, in the X direction, and that could be scattered off, you know, in the direction. Well, it's hard to show on the screen, but it's in the YZ plane and perpendicular to the direction of travel. This is the electric field. So it's moving off kind of into the screen, so to speak. Well, I'm not going to try and beat that to death because spatially it might be easier just to think about it. Well, this is the transmitted light that goes through, reaches the eye, but some of the light has been removed now. This part of the light is being removed because it's no longer moving in this direction. It's moving in the YZ plane now. Okay, and that's what accounts for polarization of sunlight. So here is your eyeball, and this is the part of this scattered light that's going to be moving in the Y direction that then eventually gets to your eyeball. Okay, that's the part that's getting to your eyeball. That's moving in the Y direction. All right, the part of this. Okay, anyway, so the big point here is some of the sunlight was scattered at this point, re-radiated perpendicularly into your eyeball. That's the point. And it's only the part that's along the z-axis that's doing that. It's not along the, the part that's vibrating along the z-axis and transmitted then along the y-axis. All right, so that is scattering in basic, and now we want to look at some of the particulars of, what light is actually scattered. So let's consider that a little more carefully. Okay. Well, it turns out that if the scattering particles, the oxygen or nitrogen molecules, are a lot smaller than the wavelength of light, then the scattering phenomenon itself decreases with wavelength in this manner. 1 over, it's proportional to the inverse of lambda to the 4th power. So as the wavelength gets smaller, as this gets smaller, that factor decrease raised to the fourth makes this a very large number. Okay, so now oxygen and nitrogen molecules, they're only about 5% the width of light, the extent of light. So it meets the first requirement, that it is effectively scattered, and according to this relationship. And so if we consider now how much more blue light is scattered than red light, we can just put the wavelengths into a ratio, 700 to 400, approximately. All right, red light is usually around 700. So since it's inverse, we do the red over the blue. You can do the other way too, just depends how you want to look at it. But this ratio, this fraction to the fourth power, well, that's 9.4. So what that says is there's about 9 times as much blue light scattered as red light. So when you look up in the sky and see the blue sky, you're seeing sunlight. You're seeing predominantly blue though, and so the sky appears blue. Isn't that awesome? Now, if you're looking through, here's the observer looking through a whole lot of atmosphere, and that atmosphere is given the opportunity for a lot of the blue light to be extracted, to be scattered out. By the time the sunlight gets to your eye, it's been removed of the low wavelengths, and only the long wavelengths are left. So the white light with blue and maybe even green, appears reddish. So that's pretty awesome. That's why the sunsets are reddish. And water particles, by the way, clouds, they're very large. They're much larger than the wavelength of light. So they scatter wavelengths about equally. They don't follow this relationship. And if they're all scattered equally, it makes them appear white. And so that's why clouds are white. Let me just finish with this clarifying graphic, hopefully. So here we have the sun. And, if you're an observer here on Earth looking up at the sun, you're not going to see, you're going to see the light having had some of the blue light scattered off. But basically, the sun goes kind of from white to yellow, is why we see a yellow sun. Because if you were outside of the atmosphere, it would basically be white. Astronauts see the sun as a blinding white light. We see it as yellowed because of some of the blue light extracted out. But you don't see that scattered blue light. But light from different angles here, the scattered blue light, some of it will reach you, and you'll see blue sky and blue sky. Now, when the sun is low in the sky and you're observing the sun, it has all this atmosphere to go through, taking out predominantly the blue, but then, to a lesser extent, the green light is scattered as well. So it's a gradient, so to speak, of removal of the short wavelengths. And by the time that sunlight gets to you, it's been pretty much reduced significantly of the short wavelengths, and you see the red sunset. And isn't it beautiful?